Sails are the engine of a sailing boat, and like any engine they need careful preparation and tuning to get the best performance, and ultimately to get the boat moving through the water quickly. This program is aimed at helping you trim your sails in relation to the weather conditions, and therefore improve your boat speed. However, before we explain the techniques, it's a good idea to understand how a sail works and what makes it more efficient. The sails act in many ways like an aeroplane's wing. They're shaped to maximise lift and minimise drag. Different conditions demand different shapes to optimise these two parameters. In light winds, drag can actually be induced to increase the performance. So how does the sail work? When the air flows over the sail or wing, the air flowing over the curve travels further than the air on the other side, because the parted air particles have to meet at the other end. The air flowing over the curve must therefore travel faster. If not, a vacuum would exist. This faster flow creates low pressure and lift. The faster the flow, the greater the lift. On a sail going to windward, this exerts a large unwanted side force, or heeling, and a relatively small forward force. The keel helps to counteract the unwanted side force. And in the keel we can do some work, particularly in the area of the leading edge, where it's important to have a smooth and a fairer shape as possible, and some work in this will improve the boat's performance. The keel works because the heeling force makes the boat go sideways through the water, a leeward motion, and this changes the symmetrical shape of the keel into a foil, which gives the boat lift and therefore an ability to go to windward. And here we have a classic example of what we don't want to see. The leading edge of this keel would break down the water flow so that the water would not attach to the leading edge of the keel. The lift wouldn't develop very well and the boat wouldn't perform to windward as well as possible. And this would apply equally to the rudder, because that in itself is a lifting foil. The combination of a genoa and a mainsail helps extend these forces greater than the sum of the independent forces, and the boats that set sails as one unit will go faster. The genoa sails in a relative lift and the main in a relative header. The shape of the sail is determined by its draft and the relative position of the draft. There are many other parameters, for example, horizontal camber, twist, angle of attack, and finally the vertical camber distribution. The objective of a sailmaker is to create a fast shape that will perform well in a variety of conditions. To demonstrate a desired shape, let's take a closer look at the draft. The draft controls the power, the acceleration, and the drag. Again, we can use the comparison of an aeroplane, which in this diagram has its flaps down with the engine on full power. The aeroplane doesn't reach maximum speed, but it gets maximum lift. As the plane's speed increases, the flaps are pulled back and the maximum speed is achieved. In a sailing boat, this effect not only increases speed, but also gives better pointing ability. A deep sail is best for acceleration and therefore better immediately after attack or to power through waves. A flat sail will be faster in smooth water or when sailing at high speed. You could think of it as a deep sail as low gear and a flat sail as high gear. The position of the maximum draft is generally about 45% in mainsails and slightly forward of this at 40% in genoas. The horizontal shape, which is taken from the luff to the leach, is designed with a fair curve to promote laminar flow, which means the air flows smoothly over the surface. Beyond 50% of the chord length, the flow becomes detached and turbulent, creating drag. The fine-tuning of setting the sails is aimed at reducing this drag. As I said earlier, when both sails are in tune with each other, the combined attach flow is greater than the two individual sails can develop. Okay, here we have a Sigma 38 Genoa, which we are going to point out two specific items. First is the telltales, which you look at when you're sailing to windward, and the second is the speed stripe, the red line here, which allows the camber of the sail to be looked at and observed. This is very important for different wind conditions where
you will increase the luff tension to get the correct sail shape as the wind speed increases. As the wind speed increases and you take the tension, it pushes cloth forward, which the headstay will push back, allowing the correct shape of the sail to be developed. And this is very important to adjust for different wind conditions the relative luff tension so that the shape of the sail stays correct.
A great deal of expertise goes into making the modern sail. As you would expect, computers are used a great deal. Software has been developed over a number of years to identify what is a fast shape. Here you can see a design for a racing mainsail. We can see the flow lines which simulate what will happen for a given wind strength. Now, if we add the Genoa, we can study the combined effect. We know that the wind changes the shape of the sail, and we can build the sails to compensate. This program will show us the changes according to the wind strength. The moulded shape is the yellow line, and the red is the flying shape. We can also use the computer to identify a potential weakness. Here it's shown up in red, which indicates the area which is overstressed. So we know we have to extend the reinforcing patches higher, even before the sailmaker started the sail.
Okay, we're going to look at some different sailcloths now, all of which are the same weight, but will be used for different purposes. And we're trying to show the differences that are there and how some of them look very similar but actually have very, very different performances. We start with the classic Dacron, and we'll say that this has a strength and a durability of 100. We move to a more racing-orientated fabric where there is mylar on the outside of both sides with an internal polyester substrate. So basically both sails are made of polyester, but completely differently. This has a strength of 20% greater than the Dacron, but its length of life would probably be half. We next move along to another mylar, which will look, in fact, very similar to the Dacron, in the sense that this has Dacron on both sides of a mylar center. This has the benefits of both worlds. We get the durability of the Dacron working with the strength from the mylar, and this would be used for slightly heavier boats and cruising sails. And finally we have, for the pure out-and-out racing sails, the Kevlars which are used, where you have a woven Kevlar with a diagonal reinforcement and a mylar film on the outside. Now, I'll emphasize all these weigh exactly the same. This has at least double the strength of the Dacron and would have the same length of life.
These materials are used to help us get the desired shape, sometimes exploiting the properties of different types of material or different weights of a similar material in the same sail. Again, the computer helps us predict what is going to happen. Wind increases in velocity and changes direction with height. These characteristics must be allowed for in the design of the sail. The vertical distribution of the depth helps develop the power from this accelerated and twisted air. The other factor affecting the vertical shape of the sail is the twist, which should match the more open apparent wind angle of the stronger breeze higher up. The shape of the Genoa and the mainsail vary not only in the position of draft, as I talked about earlier, but Genoas are generally deeper than mainsails and more difficult to adjust. The great advantage of a Genoa, if you're on a keelboat like this one, is that when it's overpowered, you can change down to a smaller one. Large overlapping Genoas are designed with a flat or straight shape aft to allow the air to escape easily. This area is called the slot. Any air that interferes with the flow over the back of the main creates more drag. It's a good idea to ensure that the crew avoid sitting or standing in the slot. Therefore, as the shape of the Genoa is mainly in the forward section, efforts in trimming are concentrated in the control of the front section, using speed stripes and tails. The mainsail has a more even shape throughout. The leech is very important, affecting pointing ability, helm as well as speed. The sails have been designed and constructed to cope with a variety of conditions. So now it's up to the crew to set the sails according to the conditions of the day.